So this is the first example. Figure 1 depicts a moment of magnitude 2 kilonewton meters exerted on a rectangular cross-section in the direction that is shown in the figure. So you can see the direction with the angle theta. And then you are asked to determine a few things here. So the first thing, for theta 0, determine the stress at point A. So we want to know what is the stress at point A, and this is a bending problem. So obviously we are talking about axial stress or normal stress in x direction. So it's sigma. It asks you for stress at point A and whether it is tension or compression. So in order to solve this, we assume theta is 0. If theta is 0, that means then the moment you have would be 2 kilonewton meters only in this direction. Now, if you have a moment like this, and if you use your right-hand rule, you can imagine that it would push A in, and then if you had a point here, it would pull it out. So the stress would look like this. We expect the stress to be compressive. Now, all you have to do is to use the formula for the stress. So for part A, sigma is, or let's say sigma in general, is my over I, and then you need to pay attention to the sign. Again, here in this example, if y is positive, we need a minus because it's a compression, and if y is negative, it's positive. So we need that minus sign, but pay attention that in this formula now, this is mz, so this is m with respect to z-axis, and this is I with respect to z-axis. And then basically y is the distance from z-axis. This is all you need to pay attention to. And if you do that, well, it's very simple to calculate this. So Iz would be 1 over 12 bh cubed again. But then in this case, b is the width, which is 30 millimeters. H is 50 millimeters, it's the height. The maximum distance, or the distance for A, is 25 millimeters. And the moment is just 2 kilonewton meters. So you insert all of that, and then your stress at point A would be 160 megapascal, and that is compression. Okay, so that's the first part of the question. Your moment is, your stress at point A is 160, and that is compression. Do you have any question about this? All right, so we do exactly the same thing now for part B. Now for part B, you are asked to do the same thing, but now assume that theta is 90. So if theta is 90, then your moment would be like that. Now, if your moment is like that, and if you use your right-hand rule, it tells you that it basically pushes this point inside and it pulls point A outside. So you would expect a stress distribution which looks like this. So basically at point A, you would expect a tension, you would expect a plus sign. You do exactly the same thing. You would say stress is equal. Now, M is with respect to y-axis. Distance is from y-axis, which is z. I is with respect to y-axis, so IY. And then you don't have a sign difference, so you would just get a plus here. And basically that's what we want to do. So if you do that now, like before, IY would be 1 over 12 BH cubed. But remember, now we are looking from a different from that other direction. So now B is 50 millimeters and H is 30 millimeters. And the distance Z for point A is the maximum distance in the Z direction. So that would be 15 millimeters. And M is again 2 kilonewton meters. So if you do that, you would have 266.7 megapascal, and that would be tension. Okay, so this is the answer to part 2. Do you have any question? Okay, in part C, it says if theta is 45 now, determine the stress. So we do exactly as we did before. For this problem, we need to calculate M with respect to Z axis and M with respect to Y axis. M with respect to Z axis would be M cosine theta, and M with respect to Y axis would be M sine theta. And if it is 45 degree, by the way, they are also equal because cosine theta and sine theta are equal. And then all you have to do is to take each of them and put them into their own formulas. Okay, so the first one, mz, you put it here in this formula. My, you put it in this formula. Then you calculate a stress for each of them and you add them up. So if you do that, you would basically have, for part C, you would have sigma equals 75.4 megapascal. Do you have any question? Good. So we have done this. Now in the next part, it asks you what happens, or if we want the stress at point A to be 0, what should be the theta, the angle theta? That's what we want to answer now. So I do it in different color. We are looking for a theta such that the stress at point A is 0. Now, remember, if we just use these formulas that we had here, basically what it tries to ask is that if you assume theta is unknown and you replace these formulas, so let's call this, maybe I call this sigma 1 and I call this sigma 2. Now, assuming that these are the formulas, all you have to do is to set sigma 1 plus sigma 2 equals 0 and calculate theta. If you do that, theta would be almost 31 degree. Okay, so it's really just one equation, one unknown. But if you have done that previous part correctly, this should be very, very simple. Do you have any question? All good? Okay, so we have done this. Now, in the next part, I use green color. No? In the next part, it asks you again, if theta is 45, compute the angle of the neutral axis. So where is the neutral axis? Remember we had this neutral axis alpha thing? It just asks you for that. And if you remember, we have learned this before. So we said the neutral axis line is basically the line where, you know, sigma of the first system, this is what we just called sigma 1, by the way, plus sigma of the second system, this is what we just previously called it sigma 2, it's 0. So if you assume these two are 0, from that you can calculate alpha, and also you may remember tangent alpha was Iz divided by Iy tangent theta. So if theta is 45 degrees, this is just simply 1. And then basically tangent alpha would be Iz over Iy. So tangent alpha would be, in this case, 25 divided by 9, which tells you alpha is almost 70 degrees. Okay, so this is also the answer to the last part. Do you have any question? Is everything clear? All right, so then I go to the next example. I clear the page here. So that was our first example. The second example is here. Consider the simply supported aluminum beam shown in the figure. E is 70 gigapascal. The beam has a T-shaped cross sections. Determine the support reactions AY and BY. So there would be reactions here that we need to calculate from a free body diagram. Determine the location of neutral axis Y bar. And then again, the coordinate system Y is given, so you are asked to calculate Y bar such that it starts from the bottom. Determine the moment of inertia I of the cross section around the neutral axis. So that's something we always need to do. Determine the equation of the elastic deflection curve. And then it also gives you a sort of a hint that if you use discontinuity function, it's preferable, and you don't have to use your EI. It just asks you to calculate them sort of, you know, as parameters. Determine the magnitude of deflection at x equals 5. Now you will need to plug in these values. And then at x equals 5, so the two parts, it asks you to calculate the transverse shear right above and right below the line C prime. So it asks you what is transverse shear exactly here, a bit up, and what is it here exactly a little below. This is what you need to do. Now, it's actually a very simple question. The fact that you have multiple parts, it's more to give you a hint, to give you a direction. Otherwise, if we asked you to calculate this, it's basically the same thing. You need to calculate the reactions, you need to calculate I, and so on. So we did it stepwise to make it simpler, basically. Now, the reactions from the support, it's very easy. If you just replace the distributed load by one load here, you would get like 12 kilonewton. So you would need two reactions such that the sum is 12 kilonewton, and then the distance here, it would be 1.5, and here this would be 8.5. So the ratio between them should be 8.5 divided by 1.5. And if you play with that, you would get AY to be 1,800 and BY would be 10,200. And then again, if you pay attention, the sum of these two is also giving you 12,000. Okay, so that's the first part. We know AY and BY. Do you have any question? Now, the second part is just calculating the neutral axis for the cross section. So for the neutral axis for a cross section, you just use your typical formulas. For each part, you calculate its centroid, multiply it by area, and divide all of that by sum of the areas. The cross section is very simple. So you would have a part at the bottom with its centroid exactly in the center, and then you would have this part on top, which is a similar part again with the centroid at its center. So if you do that, you would have your distance y bar, which is 212.5 millimeters. Okay, so this would be 212 times 0.5 millimeters. Determine the moment of inertia, exactly the same story for the moment of inertia as before. So it's just, you would say the moment of inertia for the whole cross section is the sum of moment of inertia for each part with respect to its, let's say, centroid, plus area of each part times distance of neutral axis squared. So that's your generic formula. And if you just insert the parts for moment of inertia, you would have 5.34 times 10 to minus 4 meter to the power 4. Is that clear? All right. So if you have any question, please feel free to just interrupt me. Now, the next thing we want to do is to calculate the deflection. So if you remember, and I'm going to use these discontinuity functions, but then again, it's more like a luxury. So for part D, I'm going to use discontinuity function. And then the distributed load, if you write it using the McCoy brackets, it would look like this. It's minus 4,000 times x minus 7 to the power 0. So what does it mean? It means that if x is less than 7, that means you are here. The argument here would be less than 0, so that just gives you 0. If x is more than 7, the argument would be a number that is more than 0. A number to power 0, it's just 1. So basically for any point here to here, you get a W minus 4,000, and for any point from here to here, you get W 0. And that's exactly what you want. So once you have that, then you have basically solved it. All you need to do is to just integrate this. You integrate this, you would get minus 4,000 x minus 7 to power 1 plus C1 maybe. But then instead of C1, you can imagine that if you assume x equals 0, so if you assume x is equals 0, you get just again 0 here. So C1 is the shear force at x equals 0. Shear force at x equals 0 is exactly AY. Okay, so for that reason, we can just, instead of C1, I can just write plus 1800, which is AY. Okay, once you have that, now you integrate this again. So mx would be then minus 2000 x minus 7 to power 2 plus 1800x plus, again, a constant. Let's call it again C1, if you don't mind. We can call it C1, but let's again assume that x is equal 0. If x is equal 0, this gives us 0. This gives us 0. So C1 here now is just the moment at x equals 0. So what is the moment at x equals 0? It's just 0 because it's a joint. It's a pin support. So C1 is 0 here. So that's your moment equation basically. All right, so now that you have the moment equation, what you need to do is to use that to calculate deflection. And for that, remember, the formula here is EIV double prime equals M. Now, all you need to do is to insert M into this, and then you need to integrate twice. So that's what I want to do now. Basically, what you would have is EI V double prime equals, and then I'm going to just pick exactly the function that I had here and bring it here. So all you need to do now is to integrate this. So EIV prime would be minus 2000 divided by 3, x minus 7 to power 3 plus 900 x squared plus, again, let's say now a C1, which later we defined from a boundary condition. And now you integrate again, you would get EIV equals minus 2000 divided by 4, which is 500 divided by 3, x minus 7 to power 4 plus 300 x cubed plus C1x plus C2. Okay, now that you have this, all you need is to use boundary conditions to compute C1 and C2. The boundary conditions are that V at x equals 0, so deflection at x equals 0 is 0, and the derivative of and the deflection at x equals 10, or at the end, is also 0. These are two boundary conditions. You have two constants, and you can just calculate them. If you do that, you can clearly see that C2 is actually 0 because you just replace it and you see everything is vanishing. And C1 is minus, if I'm not mistaken, is minus 28,650. All right, so this is all you had to do for this. If you really want to kind of expand it, you can also do that. You can say V equals 1 over EI minus 500 divided by 3, x minus 7 to power 4 plus 300 x cubed minus 28,650 x. This is your deflection function. Do you have any question? Okay, then it asks you to calculate deflection at x equals 5. So all you have to do is to insert x equals 5 in your deflection function, And if you do that, you get, by the way, it asks you for the magnitude of deflection, so you may want to just put it in absolute value. It's going downwards, obviously, right? So it's a negative, it's a minus number, but it asks you for the magnitude. So if you want, you can put it in absolute value. And if you do that, this would be 2.83 millimeters. Okay, so it's going to be, I don't know, the thing will deform like this maybe. And we are actually calculating the deflection here at 5. This was that. Do you have any question? Okay, so the next thing you want to do is to calculate the transverse shear. And I calculate transverse shear for parts F and G in one shot, basically. So transverse shear formula is τ equals VQ over IT. Now, we have I already. What you need is the shear force. And at x equals 5, it's here. The shear force is exactly the same as AY. So it's 1800. So you have shear force, you have moment of inertia, thickness and Q are remaining. Now, if you talk about this line, Q is the moment of area for the area above that line with respect to the neutral axis. So this is Q for this, whether you think about part F or part G. So for both parts, we have the same Q. And that Q, if you calculate it, it's going to be 2.18575 times 10 to minus 3. So that is the Q that you need for both parts. Now, if you think about a line slightly above that, let's say the section CC prime, thickness would be 250 millimeters. If you think about the line just slightly below that, then thickness would be 10 millimeters, 100 millimeters, 0.1 meter. Okay, so that is the only difference basically here. For part F, thickness would be 250 millimeters or 0.25 meters. For part G, T is 0.1 meters. That's the only difference. So if you do the calculations for part F, the shear stress would be 29.5 kilopascal. For part G, so slightly below, it would be 2.5 times larger because the thickness is 2.5 times smaller, and that would be 73.8 kilopascal. So that's that. That's really the answer to this question. Do you have any question?
I'm not sure that if I understand why the Qs are the same. Could you please explain it again?
So we are talking about the cross section here, right? This line. Now, if you remember for transverse shear, we said if you have a line, so for instance, if I ask you what is the shear stress here, the Q would be the Q of area above that line all over until the top of the beam. Okay, so that would be that. Does that make sense? So you are looking for the moment of area of that section, which is red now. Now, for the two parts, we are talking about this line. So the area above this line is just this. Now, if you are just slightly above or slightly below, it doesn't matter. The area is the same area. Does that make sense?
Yes, hocam.
Yeah.
Thank you.
And then for the area of that thing, by the way, it's relatively simple to calculate the Q. So you know that, let's say, your neutral axis is here. So you would have this distance from the neutral axis, right? And then you know the area. So basically it's very easy to calculate the moment of area for that anyway. It's basically area times that distance in this case. And that distance is, yeah, it's 0.3, because 0.3 is here, right? It's 0.3 minus y bar, which is 0.2125. And then the area is just 0.25 times 0.1. And if you do that, you get your Q, which is, yeah, I think I said that, it's 2.1875 times 10 minus 3. Yeah, thank you for the question. Do you have any question? All right, so this is again another example. So we have that. Let's go to the next one. The next one is about using the, let's say, the energy methods to calculate the deflection of a structure. It's essentially exactly the same as the examples we did in the lecture, so I don't think I have to go into details. So you have a truss structure with a load at point C. So you have a force F downwards here, and all the members are identical with cross-sectional area A, Young's modulus E. Okay, so everything is EA. Determine the support reactions. Using the method of joints, determine the internal forces in members and then indicate if they are compression or tension. Determine the vertical deflection at point C. Now, this is very nice because if we want the vertical deflection at point C, we actually have a force applied at point C in the vertical direction. So your conservation of energy, our usual approach would just work. So that's what we do. Then it also asks you to determine the horizontal deflection at point E. So you want to know how much it deforms in the horizontal direction. And this is point E. So in order to do that, we need to apply a virtual force. If you remember, we apply a virtual unit force of 1, and then we do that in the horizontal direction. And then it asks you if the direction of the external load is reversed. So if I just apply the force in the opposite direction, what do you think VC and UE will be? In which sense are they going to change? Okay, so it's a very simple problem. It's just calculation really and method of joints. I just give you a few hints. So one thing that it asks you to calculate the, the reactions of the supports, which you can do. So if you just do that, you would have, let's say, dx, dy, and ay. Maybe you have a good feeling that dx must be 0 because there is no horizontal external force on the system. So dx is 0. You don't even really have to calculate it, it's gone. Then you have dy and ay. So you write the equilibrium of forces in the y direction, equilibrium of moments, and you calculate that. If you do that, then dy would be 1 over 1 plus square root of 2f, and ay would be square root of 2 divided by 1 plus the square root of 2f. Now, when you want to calculate the reactions or the internal forces of each member, you just use method of joints, and I'm not going to repeat the method of joints here. For now on, you can just imagine it's FDB, this is FDC, this is FBC, and this is FBA, FCA. Now, you would also have FDE and you would have FEC, but maybe again, you should have a good feeling that these are both zero. Why they are zero? Because they have this 90-degree angle connection. So these are both zero force members. So the problem is not as complicated as it looks really. These two members do not exist. Okay, not in the first part basically, right? In the second part, it's different. In the second part, you apply a unit force and then this would come to play. But for the first part, you don't have to worry about that. Okay, so again, as I mentioned, you just calculate all the F's from method of joints. And then what you need to do is to draw the typical table, the famous table that we just drew previously. And using the conservation of energy, you need to calculate the deflection at point C. Now, the deflection at point C, if you call it VC, now the external work or external energy would be 1/2 times VC times F. So deflection times force, that's external force. Your internal energy is sum of 1/2 delta F. So delta for each member, so let's call it delta IFI for each member. For each member, delta is again FL over EA. And all of them, they have the same EA anyway. So that's all you have to do. You basically need to calculate all these F's. Again, these two are zero, but if you want, you can calculate it. And then you have a sum here. So you calculate your internal energy, you calculate your external energy with respect to VC, you set them equal. And if you do that, you can calculate your deflection at point C. So you would say UE equals UI. And that gives you the deflection at point C, which is in this case almost 3, so 3.034 FL over EA. So this is the part C, where we used only conservation of energy. Does that make sense? Do you have any question? As I mentioned before, method of joints, we learned it at the beginning of the semester, but as you can imagine, it's also very handy here. So it's important. Make sure that you can solve these forces. But once you have them, it's really the technicality, the next part. Okay, so that's the first part. Any question? Now, we also have the second part, so part D basically. We want to now calculate the deformation or the horizontal deflection at point E. So I'm going to do this in red. Basically, what we want to do now is to assume that there is a force of 1 here. And because of that force of 1, now you need to calculate again each of these. So what is FDE? What is FEC? What is FDB? So all these small f's with red colors, these are the virtual forces in each member. So you need to calculate them. Okay? So once you calculate all of these, then it's very simple. Then you basically do exactly the same thing as we did before. So previously we said UE was equal UI, but what you want to have now is something like basically the change of U is equal to and that change is the change that you get due to the force 1. So due to the force 1, the external work that you would have would be 1/2 of that deflection of point E, which you are looking for, times force 1, and delta UE is the sum over 1/2 of all these virtual forces times their deflection. So it would be now Fi, if you want, times delta I, but then delta I is let me maybe write it with a green color. So it would be Fi times Li divided by Ea. Okay, so this is more like a real displacement. This is like a virtual force. But once you do this, and then again, previously we did that in a table, you can calculate that. It's just a calculation step. If you do that, you would have minus, so you would have UE equals minus 0.623 FLEA. And then again, minus means, pay attention to the minus, it means that it is deforming in the opposite direction of the applied force. Okay, so this would be the direction of the deflection in point E, in the horizontal direction. Do you have any question? Very good. So the last part of the example is fairly simple. It says if the direction of the external load is reversed, what happens to the sign of VC and UE? You can calculate, or you can sort of answer that analytically, or you can just sort of answer it intuitively. So intuitively, you can imagine if you have a force that is inverse, then the deflection would be also inverse in sign, right? So instead of minus, you get a plus. But also analytically, you can see that. You can see here you have F. So if instead of F, you had minus F, obviously you get a deflection which would be minus of what you have. Okay, so in this example, it asks you to argue, and then that would be your argument basically. So VC and UE would be also reverse. And then as I mentioned, basically the reason is that you have this sign Fi here, so you would have a minus Fi, which clearly gives you a minus UE. Okay, so that would be your argument or analytical argument, but intuitively that makes sense, obviously too. Do you have any question? All right, so this was another example, and as I mentioned before, this type of examples are important, so make sure that you know how to solve them. But there is really not much complications that I can introduce to this. It's either conservation of energy, so something like this, that the force and points are exactly the same direction and points, or you need to use principle of virtual forces. But other than that, it's just method of joints and being careful with signs and numbers. The last example is here. Consider the bent shaft AB. So you have a shaft here, AB, depicted in the figure, which has a circular cross-section with radius 20 millimeters. The shaft is loaded as shown at B with a 200 Newton force in X direction and is fully fixed at A. Determine the magnitudes of the resultant internal loadings on cross-section C, so here. Determine the magnitudes of total normal stress and total shear stress at point D and at point E. Okay, so this is the example basically. And then the centroid of a semicircle is located at a distance 4r divided by 3 pi away from its base. So if you have a half circle like this, you know that the centroid is at the distance 4r divided by 3 pi. That's what you need. All right, so basically what I am asking you to do is to calculate stress state points E and D. And in order to calculate stress state at points E and D, you need to calculate the internal loadings, and that is the forces and moments at cross-section C. So you calculate all the forces and moments on that cross-section, then you calculate shear stress and normal stress at D and E. This is exactly what you need to do. So it looks like a complicated example, but it really is not. So if you just look at the force here, you can imagine that at this section, you would have that force. So the force is 200 in the X direction. So you want to calculate Fx, Fy, Fz. Well, that's that. So it's 200, 0, 0. Then I ask you to calculate Mx, My, and Mz. Okay, Mx is 0. There is no moment with respect to x-axis. But if you multiply the force here with the distance, okay, so you can see this is a distance here. So the distance has two parts basically. Due to the, let's say, due to the distance with respect to the z-axis, you get a moment with respect to y-axis. Due to the distance with respect to y-axis, you get a moment with respect to z-axis. But the moment with respect to x-axis is 0. So your My would be 50 Newton meters and Mz would be 100 Newton meters. Okay, so now you have everything you wanted. On this cross section already, you know the force in x direction, you know the moment in y direction, and you know the moment in z direction. Now, the moment in y direction, you can imagine it's a moment in this direction, right? So this is your My. It is basically causing a torsion. Okay, so you have a torsion problem. So this will cause a torsion. Your moment with respect to z-axis, it is causing a bending problem. And then the force with respect to x direction, this is basically a transverse shear problem. So the formulas you would need is tau equals VQ over IT. For torsion, tau would be TR over J. For bending, sigma would be m y over I, and then again, maybe you need a minus sign. You should pay attention with the sign. That's it. So basically, that's how you're going to solve this problem. You split this problem into these three types of problems. So for part B, we want to talk about point D first. Point D is on top here. Your normal stress is 0. So again, pay attention. You would get normal stress because of the bending problem, but your moment is with respect to that axis, it's with respect to Z axis. So it's on the axis of the moment. So stress, normal stress is zero. Your shear stress is a combination of two types of stress. And then maybe I talk about its absolute value because it asks you for magnitudes. So it would be TC over J, it's your torsion problem, minus VQ over IT. And from the dimensions and the values that we have, we can calculate these and you would get 3.77. I just explained that in a moment. So V is again your shear force, and that's exactly what we have as 200. Q is your moment of area, and for moment of area, if you think of this problem, so this would be your area. It's a half circle. Okay, so it's a half circle, and then you can calculate that using the distance that you have here. So Q would be 5.33 times 10 minus 6. Thickness would be essentially 2 times radius is the whole diameter, which is 0.04. And moment of inertia, I, well, you need to calculate I with respect to the neutral axis, so that you have it. It's 1/2 of J, right? So I is, for circular cross-section, is 1/2 of J. That's 1/2 of J itself is pi over 2C to the power 4, right? So that's J here. And T is the torque, which is the moment with respect to y-axis, that's your 50. Okay, so that's what you have. And basically, if you do that, if you insert the numbers, you get 3.77 megapascal. Do you have any question? Is everything clear? Okay, so I think there should have been a question because I didn't answer one thing. So there is this thing about the minus sign in between. Nobody asked really. You should pay attention that my here that we say it's 50 Newton meters. It depends how you are looking at it. So if how to put it that properly. So basically, if you are looking at this cross section, assuming that you're cutting it like this, that moment is something like that, okay? So basically, it would result in a shear stress that would be in the opposite direction. of the shear stress that you would get from your VQ over IT. That's why they have opposite directions, and that's why we subtract them. Okay? You can imagine if the force that you had here was 200, then you would need to 200 in the opposite direction, you would need to add them. Okay? You should just pay attention to that. But here I kind of wrote the magnitudes because it asks you only for the magnitudes. But when you want to calculate this, you need to pay attention to the signs. All right, so that's for point D. Now for part C, we do exactly the same thing. It's easier because we have done the more difficult part of the problem. So for point E, you would have the bending stress, which is again mz divide mz distance from z axis, which is y, and then maximum x, and that maximum x is c, divided by iz. So if you do that, you get 15.91 megapascal, and then tau e, and then again, these are magnitudes because the question specifically asks for magnitudes to make it simple for you. And then you would also have this torsion problem again, Tc divided by J, and now you get 30.98 megapascal. So for point E, again, due to torsion. But due to the VQ over IT, for point E, you would get 0 because it's, again, the force here is in this direction. So Q is 0. It's exactly the point on top of the cross section when you look at that. So for point E, Q is 0, and then therefore you don't get additional shear stress at point E. You just get 3.98 megapascal. Yeah, that's that. That's also the answer to this question. Do you have any question? Everything clear? Very good.